In 1952, I spent a year teaching physics in Brazil, at the Centro Brasileiro de Pesquisas Físicas in Rio de Janeiro. I arrived expecting to find students eager to learn, institutions building scientific capacity, a community engaged with the fundamental questions of nature. What I discovered instead was something far more disturbing, something that revealed a profound failure not just in Brazilian education, but in how we teach science everywhere. The students could pass examinations, they could recite formulas, they could solve textbook problems, but they knew nothing, absolutely nothing about physics. And the worst part was that nobody, not the students, not the professors, not the administrators, seemed to notice or care. Let me tell you what I mean by knowing nothing. These students could tell you that light travels in straight lines. They could write down Snell's law relating the angles of incidence and refraction. They could calculate how light bends when passing from air into water. Every examination question about refraction they answered correctly. So one day I asked them a simple question. I asked, when you look down at a swimming pool, the water appears shallower than it actually is. Why does this happen? Silence. Complete silence. No one could answer. I tried rephrasing. I asked about the path light takes from an object underwater to your eye. Still nothing. These students had studied optics. They had passed tests on refraction, but they had never connected the equations to the actual phenomenon happening in front of them every time they looked at water. This wasn't ignorance of an obscure detail. This was a complete absence of understanding, despite extensive exposure to the material. They had learned physics the way one might memorize a foreign language phrase book without understanding grammar or meaning. They could reproduce symbols on command, but those symbols connected to nothing real in their minds. I began investigating. I sat in on classes. I examined textbooks. I talked with students and faculty. What I found was a system that had optimized itself perfectly for producing the appearance of education while delivering none of its substance. Students attended lectures where professors wrote equations on blackboards. Students copied those equations into notebooks. Before examinations, students memorized their notebooks. During examinations, students reproduced what they had memorized. Then they forgot everything and moved to the next course. At no point in this process did anyone ask, what does this equation mean? What physical situation does it describe? How would I verify it experimentally? Why should nature behave this way? The textbooks were equally bad, perhaps worse. They presented physics as a collection of facts and formulas to be memorized. They never explained where these formulas came from, or why anyone should believe them. They never connected the mathematics to observable phenomena. They never taught students how to think about physical situations. I found one textbook that defined something called the Brewster angle, gave a formula for it, and moved on without ever explaining what it was or why it mattered. Students memorized the formula and could calculate Brewster angles for various materials, but not one student could tell me what polarization was or why light reflecting at a certain angle might be polarized. This revealed something important about the difference between real knowledge and the simulation of knowledge. Real knowledge means you can take what you've learned and apply it to new situations. It means you understand the principles deeply enough that you can reason from them. The students in Brazil had none of this. They had only surface patterns, strings of symbols they'd been trained to manipulate according to rules they didn't understand. Let me give you another example that crystallized the problem. I asked a class, suppose you have a metal ball with positive charge. You place your hand near it, but don't touch it. Will you feel anything? One student said yes, you'll feel a force because the charged ball creates an electric field, and that field exerts a force on charges in your hand. This was good. This student was thinking. But then I asked, which direction will the force be? The student thought for a moment and said, the ball has positive charge, so it repels positive charges and attracts negative charges. Your hand has both kinds of charges, the electrons and the nuclei. The electrons will be attracted toward the ball, the nuclei repelled, so the charges in your hand will separate slightly. But there are equal numbers of positive and negative charges, so the forces cancel and you feel nothing. This answer was wrong, but it was beautiful. The student was reasoning from principles. He was thinking about what actually happens physically. I could work with this. I could point out that the attracted electrons move closer to the ball than the repelled nuclei, so they experience a stronger force, and the net effect is attraction. The student would understand because he was thinking about the physics. But this student was an exception. Most students couldn't even begin to think about the problem. They searched their memories for a formula relating force and charge and distance, found nothing that matched, and gave up. They had no framework for reasoning about physical situations. They had only formulas, and when the formulas didn't directly apply, they were helpless. I started asking myself, why does this happen? How can an entire educational system produce students who study physics for years but never learn to think physically? The answer I came to believe is that somewhere along the way, education became confused about its purpose. Instead of teaching students to understand nature, it began teaching students to pass examinations. And once that substitution occurred, everything else followed inevitably. Think about what happens when passing examinations becomes the goal. Professors structure courses around examination topics. Students study only what will be tested. Questions that don't appear on examinations are ignored as irrelevant. Understanding becomes optional if you can memorize effectively. The entire system optimizes for a metric that has almost nothing to do with actual comprehension. The Brazilian students weren't stupid. They were smart, capable people responding rationally to the incentives their educational system created. If you can pass examinations by memorizing, and passing examinations is what matters for your degree and your career, then memorizing is the intelligent strategy. Understanding takes more time and effort than memorizing, and if examinations don't actually test understanding, why bother? This explains why students never asked questions in class. I would lecture, filling blackboards with derivations, and the students would copy everything silently into their notebooks. I would pause and ask if anyone had questions. No one ever did. At first I thought they understood everything perfectly. Then I realized they weren't thinking about what I was saying at all. They were transcribing. Their goal was to capture the symbols accurately so they could memorize them later. Whether those symbols made sense was irrelevant to them. I tried to break through this. I tried asking them questions during lectures to force them to think. But I discovered they had developed a defense mechanism. When I asked a question, they would sit silently until I answered it myself. They had learned that if they waited long enough, the professor would always provide the answer and then they could write it down. Asking them questions didn't make them think. It just slowed down the transcription process. So I tried something different. I announced that I would teach the class differently. We would work through problems together. We would discuss the physics. We would try to understand what the equations meant. The students were polite but unenthusiastic. A few weeks into this experiment, several students came to me and asked me to go back to the old way. They explained that they needed to take notes so they could study for examinations. My new approach made this difficult. They were falling behind in their transcription. This moment clarified everything. These students genuinely believed that copying equations from the blackboard into notebooks constituted learning. They thought physics was a collection of formulas that you memorized and reproduced on demand. The idea that physics was about understanding how nature works, that the formulas were concise descriptions of physical principles that you could derive and apply and test against reality. This idea was completely foreign to them. I want to emphasize that this wasn't a problem of intelligence or culture. The Brazilian students were as smart as students anywhere. The problem was systemic. The educational structure they inhabited had no mechanism for teaching or rewarding actual understanding. Every incentive pointed towards superficial memorization, and the tragedy was that everyone involved, students and professors alike, seemed unaware that anything was wrong. The professors genuinely believed they were teaching physics. They covered the standard topics. They presented the important equations. They assigned problems from textbooks. They gave examinations. By every conventional metric, they were doing their jobs. But they never asked themselves whether students were actually learning to think physically. That question simply didn't arise in their framework. I attended faculty meetings where professors discussed curriculum. They debated which topics to include, how many hours to allocate to each subject, which textbook to use. These discussions were entirely about content coverage, never about understanding. No one asked, do students learn to reason from physical principles? Can they apply what we teach to new situations? Do they see connections between different phenomena? These questions were outside the frame of reference. This made me realize something about education more broadly. There's a persistent confusion between teaching material and teaching thinking. We design curricula as lists of topics to cover. We measure success by how much material we present. But presenting material doesn't mean students learn to think about that material. You can cover optics without teaching students to think about light. You can cover electricity without teaching students to reason about charge and field. You can cover mechanics without teaching students to analyze forces and motion. And this is what happens in most places, not just Brazil. The students in Brazil made this visible because the disconnect between coverage and comprehension was so extreme. But the same disconnect exists everywhere, just usually to a lesser degree. Everywhere you find students who can solve textbook problems but can't apply the same principles to unfamiliar situations. Everywhere you find students who memorize formulas without understanding their physical meaning. Everywhere you find educational systems that measure success by examination scores, rather than actual understanding. What would real physics education look like? It would start with phenomena, with things students can observe and wonder about. Why do mirrors reflect? Why does a prism split white light into colors? Why do things fall? Every topic would begin with a question about nature, something that makes you curious. Then you would reason carefully from basic principles toward an explanation. You would make the reasoning explicit, showing why each step follows from what came before. You would connect the mathematics to the physical situation at every stage. And critically, you would teach students to do this themselves, to look at a phenomenon and figure out how to think about it. This approach requires something that's very difficult to do in a classroom. It requires students to struggle with problems they don't immediately know how to solve. It requires them to feel confused, to try approaches that don't work, to gradually build understanding through effort. This is uncomfortable. Memorization is much more comfortable because it creates the feeling of progress without the struggle of actual thinking. You read something, you memorize it, you feel like you've learned it. The fact that you haven't understood it doesn't register because understanding and memorization feel the same from inside your own head. I tried to create situations where students had to struggle. I would describe a physical situation and ask them to predict what would happen, not by remembering a formula, but by thinking about the physics. For example, I described two cylinders, one solid and one hollow, both with the same mass and radius, rolling down an incline, which reaches the bottom first. Students needed to think about rotational inertia, about how mass distribution affects angular acceleration. Most students couldn't do this. They searched for a formula they'd memorized and found nothing applicable. The idea of working it out from basic principles didn't occur to them. When I showed them how to think through the problem, they were amazed. They had never seen anyone reason from first principles to solve a problem. Every problem they'd encountered had been solved by finding the right formula and plugging in numbers. The notion that you could start with fundamental laws like Newton's second law and conservation of energy and derive the solution to a new problem was a revelation. This revealed another deep issue with how physics was taught. Students were given formulas for specific situations, the period of a pendulum, the frequency of a spring, the speed of a wave on a string, but they were never taught how those formulas were derived or how to derive new formulas for new situations. Physics appeared to them as an enormous collection of special cases to memorize. The unity of physics, the fact that a small number of fundamental principles explain an enormous range of phenomena, was completely hidden from them. I remember one student asking me how I knew so many formulas. I explained that I didn't know very many formulas at all. I knew a few basic principles, Newton's laws, conservation laws, Maxwell's equations, and I could derive most other formulas when I needed them. The student was skeptical. He asked me to derive the formula for the period of a physical pendulum. I did it on the blackboard, starting from the torque equation and getting to the standard result. The student was astonished. He had never imagined that formulas could be derived. He thought they were facts about nature that you had to memorize, like the boiling point of water. This misconception about the nature of physics is devastating. If you think physics is a collection of facts to memorize, you'll never understand it. Physics is a way of thinking about nature. It's a framework of fundamental principles and reasoning methods that let you understand and predict how physical systems behave. The formulas are outputs of this framework, not inputs. Learning physics means learning to use the framework, not memorizing its outputs. But teaching students to use the framework is difficult. It takes time and effort. It requires small class sizes where you can watch students work through problems and correct their thinking. It requires examinations that test understanding rather than memorization, which means examinations that are hard to grade and don't have unique right answers. It requires professors who themselves understand physics deeply enough to teach the thinking, rather than just presenting results. And it requires students who are willing to struggle through confusion toward understanding rather than taking the easy path of memorization. None of these requirements were met in Brazil. Class sizes were large. Examinations were designed for easy grading, with questions that had definite numerical answers. Professors taught the way they themselves had been taught, presenting material rather than teaching thinking. and students rationally responding to the incentives they faced, optimized for examination performance, rather than understanding. Near the end of my time in Brazil, I was invited to give a talk to physics professors and education officials about my experiences. I thought carefully about what to say. I could have been diplomatic, praising what worked and gently suggesting improvements, but I decided that the situation was too serious for politeness. The entire educational system was failing at its fundamental purpose, producing graduates who had studied physics but learned nothing about how to think physically. Someone needed to say this clearly. So I gave a talk titled something like Science Education in Brazil, where I explained everything I've described here. I told them that students were learning to pass examinations but not learning physics. I told them that the textbooks were terrible, presenting formulas without explanation or motivation. I told them that the teaching methods didn't work, that lecturing and transcription don't produce understanding. I told them that the examination system was measuring the wrong things. I told them that the entire enterprise was broken and needed fundamental rethinking. The response was interesting. Some people were angry. They thought I was insulting Brazilian education and Brazilian students. They defended the system and insisted that students were learning properly. But others, particularly younger professors and students, came to me afterward and thanked me. They said they had felt something was wrong but couldn't articulate it. They said my talk gave them language for problems they had sensed but not understood. Looking back on that experience now, decades later, I see it as a lesson not just about Brazilian education in the 1950s, but about education everywhere and always. The fundamental problem I encountered, the substitution of examination performance for actual understanding, happens everywhere whenever we lose sight of what education is for. It happens in physics, in mathematics, in every subject where we let the measurement become the goal. What makes this particularly insidious is that the simulation of education looks very much like real education from the outside. Students attend classes, take notes, read textbooks, solve problems, pass examinations, earn degrees. All the outward forms are present, only the substance is missing. And because everyone involved is focused on the forms, the absence of substance goes unnoticed. Students think they're learning because they're passing tests. Professors think they're teaching because they're presenting material. Administrators think the system works because students are graduating. Only when you actually probe whether students can think about physics, whether they can apply principles to new situations, whether they understand what they've supposedly learned, does the emptiness become apparent. The question is, how do we fix this? How do we create educational systems that produce actual understanding rather than simulating it? I don't have a complete answer, but I know what the key elements are. First, we need to be clear about the goal. The goal is not content coverage. The goal is not examination performance. The goal is teaching students to think, to reason, to understand. Everything else follows from getting the goal right. Second, we need teaching methods that actually promote understanding. This means active engagement with material, not passive transcription. It means working through problems where students don't immediately know the answer. It means discussion and argument and mistakes and confusion followed by clarity. It means showing students how experts think about problems, then having them practice that thinking themselves. Third, we need assessment methods that measure understanding rather than memorization. This is difficult because testing understanding is harder than testing recall. Understanding requires open-ended questions where students explain reasoning, apply principles to new situations, make predictions, and justify them. These questions are harder to ask and harder to grade. But if we don't test understanding, we create incentives for students to optimize for memorization instead. Fourth, we need professors who themselves think deeply about their subjects and can teach that thinking to others. It's not enough to know the results of physics. You need to understand how those results were discovered, why they're true, how they connect to other results, how to apply them. You need to be able to watch a student work through a problem and diagnose where their thinking goes wrong. This requires a depth of understanding that not everyone who has a physics degree possesses. Fifth, we need students who understand that real learning requires struggle and confusion and effort. The feeling of not knowing, of being confused, of having to think hard about something, this is what learning feels like from the inside. The feeling of reading something and immediately understanding it, of memorizing facts effortlessly, this feels like learning, but usually isn't. We need to teach students to embrace difficulty rather than avoid it. None of this is easy. Real education is difficult for everyone involved. It's difficult for students because it requires sustained mental effort. It's difficult for professors because it requires deep understanding and skilled teaching. It's difficult for administrators because it doesn't scale well and can't be measured with simple metrics. But difficulty doesn't mean impossible. We can do this. Some places do it successfully. The question is whether we care enough to put in the effort. The experience in Brazil taught me that you can have all the outward forms of education, classrooms and textbooks and professors and examinations without having any of the substance. You can have students who attend lectures diligently and study hard and pass examinations but who learn nothing about how to think about the subject they're studying. And most troubling, you can have this situation persist indefinitely because everyone involved thinks everything is fine. This is the real danger of educational systems that optimize for the wrong goals. They don't obviously fail. Students don't revolt. Professors don't quit in frustration. Parents don't complain. The system produces graduates with degrees who can get jobs. Everything appears functional. Only the core purpose, actually teaching people to think and understand, is missing. The students I taught in Brazil deserved better. They were smart, capable people who came to university, wanting to learn about nature. The system they encountered didn't teach them that. It taught them to memorize and regurgitate. It taught them that physics was about formulas rather than understanding. It taught them to optimize for examinations rather than comprehension. And in doing so, it wasted their time and potential. We can do better than this. We can build educational systems that actually teach understanding. We can train professors in effective teaching methods. We can design curricula around concepts rather than content coverage. We can create assessments that measure thinking rather than recall. We can help students understand what real learning requires. None of this is impossible. It just requires caring about the right things and being willing to do the hard work of real education rather than accepting the comfortable simulation of it. That's what I learned in Brazil. Not just that one system was broken, but how easy it is for any system to break in this particular way, and how important it is to remain vigilant about whether we're actually teaching understanding or just creating its appearance. The question every educator should ask constantly is, are my students learning to think, or are they just learning to pass my examinations? If you can't tell the difference, you're probably doing the second while thinking you're doing the first.